Really nice to have you all. Let's see if it is recording. It is, and let's get started. I think it is 11 on the dot. So today is wave mechanics of bound states. Yay! Bound states. Let's get this working nicely. Yeah. So this is working these days. I'm like, what's your mood? What's your mood? Awesome. What's my mood? Yeah. It's really nice to see you guys smile, and I feel more confident and more relaxed. And yeah. So thank you for that. All right. And I also overheard. Yes, please.
Oh, is that? I think you're gonna say that. You can go ahead.
Oh, good. Yes, you do it. You do it. I know what you want to do. Go for it.
No, you can go ahead.
No, please.
It's Grace's birthday, guys. It's Grace's birthday, so we're all gonna sing.
I agree. I'm going to be the choir master.
All right.
Happy birthday to you. Happy birthday to you. Happy birthday, dear Grace. Happy birthday to you. Good. Thank you so much for that. I like this part. All right. So another fun thing will be simulations of what we want to do. Yeah. So you have the web page, and you can do this simulation of bound particles. It's so cool, and it's real. How many of you have heard of quantum dots? That's the closest we have of bound states with infinite wells, and I will show you. I do the research in my lab to make use of quantum dots. They are now being fabricated. It's almost like having an artificial atom with a lot of promising applications in green energy, even in biomedical issues. So it's cool that we can, this thing that looks so artificial can be reproduced in the lab, and perhaps soon in technology. Already it is there in technology, just finding newer uses. So speaking about simulations, let me just show you. It turns out that we have it working here on this computer. So if you go here, that web page that I showed you, you can actually play with it. Can you see it right there? You tell me what to do. Let's look at one well. Okay, two wells. Yeah, let's start with one well. What does that look like? A square well, right? So we can choose things. Choose a square well, different 2D, 3D, harmonic oscillator. So you go there, decide the width, and decide which energy you want to see, and simulate it. Click on. So it kind of allows you to change the mass and see how that changes things. The depth of the well. You can also choose to see both the real part and the imaginary part and all that. So it's cool, yeah? It's really cool considering that we have real applications for those. So let's quickly see where we are and then take the quiz. So today I'll try to solve on the board with you the infinite square well in a slightly different way than the book so that you have a very good grasp of it. And every other thing, as usual, on my slides, the entire plan we have, and we are following it nicely. Homework 4 is due on Thursday, and there are 2 questions. Question 2, that means 2.34, something like that. We already did it last week, so it's just take it further. It is the step potential. And question 2.4, we are doing it today. Actually, it is based on the reading, and it just means you continue from where we stopped today. Find, for example, the expectation value of the position from the wave function that we will obtain today, that you have read about the wave function for the infinite square well. So it will just be psi star x psi for the psi that we will find for the infinite square well. All right. That's where we are. Remember to look at my slides and study further because I have more details on the slides than on the board when we work together. Usually add more math, more fillers and all that. So please go through the slides. Quiz then, and I will be sharing out the previous quiz while you're taking the current one. Oh, yes, I've seen. With the cap and the mask.
Yeah.
Change, yes. I can take it if you're ready. Thank you.
Okay.
Oh, yeah. Everyone submitted? Thank you, Nathan. All right. So we need it in terms of, let's see if I can have it there on the screen. For a bound particle in an infinite square well of width A, express the wave number k in terms of well width. So k equals n pi over A, right? That was part of the reading, right? Was it fair? Okay. So what is psi of x for the bound particle in an infinite square well? Stated using trigonometric functions. Yeah. So psi of x a sine theta or sine kx plus b cosine cosine kx. Right, so I can do it. I can rewrite it and say a. Sometimes it allows me to do it really fast. Sine kx plus b cosine kx. And we already said what k is. And we want to show this explicitly, all the details and all the arguments, so that you can do it easily. It's a very important potential. So bound particles, we will return to my slides after we do stuff on the board. So let's do it as we know how to do on the screen or on the board. Last time we did it here and people kind of liked it. Should we try it here or on the board? You don't really care. Let me try it here again and we see. We've done a few times there. Let's do a few times here and we will know which is best, which is better. So here we are. Okay.
Where's the break? We can use books.
So, number 20 what? Last time was
This would be 22.
22. So now it's 22.
Yes.
Thank you. 22. Bound particles, let's call it infinite square well. Infinite. Interesting. Square. All right. So, just to keep things tidy, I'd like to start by stating v of x or drawing the well. Okay? So, let's draw the well. What might the well look like? Let's have it. Okay? The book had this place as a, right? Let's do a over 2. And do negative a over 2, just to be different, because sometimes you read other books that do it differently. And the book said, always try to exploit the symmetry of the problem. So we've got positive x over here, and this way is negative x. So we can stay at the center of our well. The center of the well is 0. So up here is v. It goes to infinity, okay? Up to infinity, that's v. So inside, v equals 0. Big V, okay? And outside, v equals infinite. V equals to infinity, yeah? Same here. So we can state this more mathematically by saying v of x equals, in a brace, 0, where x, let's say absolute x. So positive x is less than or equal to a over 2. Less than or equal to a over 2. I hope you permit my little, so the modulus x. It will mean that negative x will be less than or equal to negative x over 2 also. Yeah. So how about this? What region is x? What region of x is the potential infinite? Yes, please, Carter.
When it's less than negative a over 2 or greater than a over 2.
Correct. So we can write it this way: greater than a over 2. Are we together? So immediately, having stated v of x and drawn the sketch, the next thing to be careful about, we do boundary conditions, even arising from the nature of the potential energy. So BCs, can I just put BCs rather than writing boundary conditions? Boundary conditions arising from the nature of the potential energy, because we can do that before even solving for psi. Is that okay? When we state it clearly, we will then use it when we need it. Okay. So look at it and think. When V equals infinite, what happens when V is potential energy, so it is energy. When V is infinite, what happens to the Schrodinger equation? What do you expect of the wave function?
To go to 0.
Sorry?
To go to 0.
It's 0 because nothing is going to be there. Nothing is going to have that infinite energy. So the boundary condition allows us to say that psi at x greater than, yeah, do we agree? X absolute greater than a over 2 equals 0. Reason. What's the reason? We said it already, but this please.
Continuity.
No, we just said not yet. We are getting there.
Okay. Because it's not going to be there.
You actually answered the previous one. Greater than, so in the region where it is infinite, psi has to be what? 0, because the potential energy is infinite. Do we agree? It's not a trivial argument. It changes the boundary conditions actually. So V is infinite. There's infinite energy. The particle cannot be there. And because of that, the next boundary condition comes in. And I think Carter is going to help with this one. Because then psi of x equal to a over 2. I can even say psi of x equal to plus or minus a over 2. Let me make it very clean and clear. Equals to plus or minus a over 2 equals what?
0.
Why?
Continuity.
Continuity with what? So continuity of psi with the other side. Do you get it now? That is the point. Continuity of psi. So psi is 0. Watch my means. So psi is 0 here because of infinite. And at the boundary, that imposes on psi to be also 0 for its continuity. Wow. That's cruel, maybe, but that's actually where the quantization will show up. And that's why I took time to make the point. Yeah. And because V is infinite, the condition of continuity of psi prime is relaxed. You got that immediately. So let me take off from there. Now we can solve the time-independent Schrodinger equation. For which region? Please. The region in which V is 0. Because we know what psi is at the boundary and where V is infinite. Now we can solve for psi where V is 0. So, negative h bar squared over 2m d squared psi dx squared plus V of x psi equals E psi. And we just agreed that in this region, let's make it explicitly clear that we are solving for psi in the region in which x is what? Less than a over 2 and negative x is greater than negative a over 2, just to be super clear. Yes?
This is a big question, but in the book, we read about, he put a scenario out there. This was in I think it was in 2.1, but
Okay.
he put a scenario and said, the problem is you need to solve a time-dependent Schrodinger equation, so we're gonna start at the time-independent Schrodinger equation. Is that why we're always solving the time-independent Schrodinger
Good
equation
question.
first?
So we actually in class wrote down the time-dependent Schrodinger equation and then used the method of separation of variables because it's easier. And from separation of variables, it was easy to focus on the time-independent Schrodinger equation. In fact, we also solved the time-dependent part and kept it there and called it, he answered the question nicely. Joey, yeah?
Wiggle factor.
The wiggle factor. Remember, the wiggle factor is in the exponent, so we can always tag it on. We know the answer. So when we solve the time-independent Schrodinger equation, we are doing it because we can easily tag on it the time-dependent factor and get the general solution.
Okay, so we always will start with the time-independent Schrodinger.
That's the most convenient.
Gotcha.
Yeah. Yes,
Thank
good
you.
point. Good question. Any other one? All right. So are we happy now? V is what here, please? 0. So we send it to 0. And we are left with the time independent. And this looks like the free particle, but it's the bound particle with no potential energy. So what is it going to be? What next? Let's rearrange it. How will it look like when we rearrange it? So, still on, what point was that? What number was that?
3.
3. Okay, so still on 3. 3 continue, so it's easy for you to write down. 3 continue. Our time-independent Schrodinger equation can be rearranged, and you permitted me to use psi double prime. So what is that now? Equals what? Negative h bar squared. Is that correct? So it will be equal to negative square root of what? 2me over h bar, right? Are you sure? I'm making lots of errors so that you can say, no, yeah, and I can see it. So what should it be then?
Everything should be squared from there.
So I remove the square and put it here. Why? Because we want k squared. So don't mix it, because I've seen. Okay. That's psi. Wow, this is good. So how do we rearrange this? So that we can solve it even without looking further. Psi double prime plus 2me over h bar squared psi equals 0. Familiar? Simple harmonic motion kind of, yeah? Familiar. So this is our k squared. So don't mix it up. In other words, we can write it explicitly. That k is what? Square root of 2me over h bar. Now, to get a solution, we need to consider energy. Look, see k here. What energy will allow us to get reasonable solutions? I make it simple. Let's do E less than 0. What will happen? E equals 0. What happens? E greater than 0. What happens? Class discussion. Which solution is going to yield something reasonable? It's a bound particle, so think about it.
No, it's just not normalizable.
I heard something good there.
Why? If it's less than
It
0.
says that because the second derivative and psi itself would both be the same sign always, it's
Right.
unnormalizable.
So we cannot have e less than 0.
What if you use an imaginary number?
Correct.
Then you could,
You could.
but it would be imaginary.
It will be imaginary, and the solution will not be, it will end up being 0 in the end.
Okay.
Just as good point. And I have those on my slides. So, by discussion, we've agreed already that this is the one that will give reasonable solutions. Good. Let's do it. In other words, our care is real. Care is real by consensus. So that the particle is a real particle stock. Otherwise, we have an infinite square world, but no particle. We want a real particle there. Are we okay? Good. So then, what's the solution? The general solution will be psi of x. Who goes for it? Who takes it? Okay. So maybe my battery and the pointer is. Let's do this. Okay. So I'm going to use my finger then. Oh, it's not just my stylus, but the screen. Okay. So let's try a new screen. I'm trying to get a new screen.
You have 5 screens now, here. And it's just frozen.
So it's not responding to me. Do we go back to analog?
Go back one more.
Okay, let's see.
Just try that one.
Let's try it.
Because that should be a slightly right there.
Yeah, let's try it again. Nothing
Oh
wrong.
wait, it says you're on the eraser, I think, doesn't it?
Well, yeah,
It's
but
trying
Yeah, I'm on
it's
the
trying to
eraser.
erase. Oh,
So I want to erase.
yeah.
See the eraser? I want to erase. Back to stylus. I want to write.
Yeah, what happens if you hit the back arrow?
I'm sorry?
On the far right of the object, it's the back
Undo.
arrow.
This one?
Yeah.
Let's see.
Alright.
Yeah.
Maybe it's
Any other ideas?
restart.
I like the ideas.
Let's just be careful.
Okay, so it's really not responding.
Turn it off and turn it back on.
So let's turn there. Nice. Whee.
Yay.
Yeah. It's good to have your plan B. How about the, yes, thank you. So we can watch ourselves turn so that we get it right. And you can make it bigger, enlarge. So. It's like always be ready for different scenarios. So we continue.
I'll make sure.
All right. So we wanted to solve for psi in that region. Psi of x will then be what? We've got a k that is real. Yeah.
A sine kx plus b.
A sine kx plus b cosine kx. Is that the only way we can write it?
No.
Okay, how about this? Just to be sure. Is this correct? Will this work? Can this work? Why not?
Because you need an imaginary part in the first one for that.
Yeah, but we can, since we can, this contains both imaginary and real. Is this not actually one of the real parts there? So it can work.
Yeah.
Yeah. It's just that it's easier to work with this since our k is real. This has both real and imaginary part. Yeah. But it's easier to work, focus on the real since k is real and we're, yeah. Yes. So, and psi squared is what we want in the end for probability. So, and once you get the real part, it means that you can assume the imaginary part. I mean, cosine, sine, the one is this way, the one is that way. So, yeah. Make sense? So we're taking this not because this does not work, but because this is real. It's the real part. So, let's keep to it then. And apply. So step 4. Apply BCs on psi in which region? Remember we said that psi has to be
It's true at x equals a over 2.
Do you remember that? We had that boundary condition in which psi at x equals x over a over 2 and x equals negative a over 2, we know that it had to be 0, right? That's what we are applying now to this general solution. So, psi of x equals plus or minus a over 2 should be a sine kx plus b cosine kx equals 0. Do we agree? Because of this boundary condition. In the well, it can be anything allowed inside, but at that boundary, that is the condition imposed on it by continuity of psi and by the nature of v equals infinite outside the well. Are we together? Okay. So then what solutions will be less boring, will be not boring? Interesting. A equals B equals 0 is obviously boring. So A not equal 0, what will that give us? And B equals 0. Let's do that one. So let's do, this is A, this is B, little b. Let's do A not equal 0, B equals 0. Is that okay? So I claim. So that means that psi will then be equal to, see, A not equal 0, so A sine kx equals 0 at x equals plus or minus a over 2. That's the result of the boundary condition. How will we make that work? Yes.
Kx has to equal 0 or pi or multiple pi.
Absolutely correct. So that imposes, that means that k must be quantized so that it becomes n pi over a. Yeah? We need that to happen. Yes.
Wouldn't it be in 2 pi over a? Because didn't we say a?
That's possible, but that's because I chose the boundary at a over 2.
But wouldn't you have to plug in a over 2 into x?
We can do that and see. This will work.
Okay.
And that's, okay, since we started with sign, let's do it explicitly. That restricts n to what? So in this case, n should be, to get the zeros, what should n be?
Positive integers.
Sorry?
Positive integers.
Positive integers, but in the case of sign, so will 1 work? Will n equal 1 work? Absolutely correct. Will not work. Jared got it. So n has to be 2, 4, 6 in this sign solution.
Oh,
That answers it for you, right?
yes.
Yes.
So if we instead chose the region for the infinite square root to be from 0 to a, would it then be just 1, 2, 3, 4?
Yes, depending on whether we are doing the sine or the cosine. Let's do it explicitly now that I have the questions. Let's put 2 there and see what happens. Yeah? For n equals 2, for n equals 2, then we get a sine. So k is what? 2 pi over a. Yeah? At where?
A over 2.
at x, because it is kx. So x is what?
A over 2 plus.
Got it. You see? A sine pi is 0. Yes. So we put 4, same thing. Because pi, sine 2 pi, sine 3 pi, yeah? 180 degrees next. All right. So that's what we do. So we now, since you have asked, this shows that we will have even solutions and odd solutions. So the sine part, in the way I set up the well, gives us the even solutions. Let's do it for b not equal 0, yeah? So sine of x equals plus or minus a over 2 equals b cosine kx equals 0. And that puts condition on k, because we cannot have b is already something, not 0. And k, remember, k was what from our initial stuff? K was square root of what? 2me over h bar. So k cannot be 0. The energy is there. We're solving for E greater than 0. So K is real. We all agree on that, right? So because of that, this imposes this condition on K. And in this case, what will N be in the case of cosine?
1, 3, 5.
Thank you. Any question? We can try it to put it in. So for sine x equals plus or minus a over 2, it will be equal to b cosine, what is our k? Which one should we try? 1 is okay. So pi over a times x. What is x? A over 2. And cosine pi over 2 is what?
0.
Yes. So we got our general solution. We can tie it together. And usually we just take one of them because it will just keep being integers and we know how to work with that. And the next is normalization. So there is a condition on our n, on our k, n pi over a. Yeah. And that means immediately that what is E? En equals what? Remember, in this formula that we had for E, when we started solving, K was equal to square root of 2me over h bar. So what that implied that E was what?
K squared h bar squared over 2m.
K squared h bar squared over 2n. Very good. So we now write K squared in terms of this. Are we together? K squared will then be n squared pi squared over a squared. And then we add the other ones. So K squared h bar squared. So that should be h bar squared, h bar squared. And then there is a 2m there. Yeah, we got it. This is what it turns out to be, the quantized energy levels of the infinite square well. Any question? Coming from boundary conditions, just the fact that the potential energy outside the world is infinite imposes that psi at the boundary is 0. And that fixes that it should come there as a wave. Those are nodes. Those are nodes. And now, energy values are restricted to what makes it 0. The energy values are no longer continuous, but what? Quantized. That then is quantum mechanics. Quantization conditions that we don't see in classical mechanics. Wow. So that was step 4. Step 5, just for completion, will be normalization, right? Yeah, and you've done some exercises on normalization. So what will be the normalized wave function? Let's just wrap it up. Psi, how do you normalize? Psi of n equals a sine k sub nx. Let's write it that way. And we say for normalization, a squared from negative a over 2 to positive a over 2 sine squared k sub n x equals what? Equals 1. And we can integrate. And to integrate this integral, to solve this integral, it's good to make a change. A substitution, a trigonometric substitution. Sine squared x dx is easily integrated as integral 1 minus cosine 2x dx. Yeah? And if you're not familiar with that integral, we can do it together during help hours. Yeah? Because you need it for the homework due on Thursday, since you will be doing the expectation value of x using the normalized wave function. Is that okay? Any question? I feel we've done the infinite square well, got our quantized solution. Psi cannot just take any value but integers. Wow. The k is corresponding to the wave number. The wave number is quantized. And actually the size of A, the width, determines the wavelength. Let's check what that implies here. Look, we said Kn is n pi over A. Interesting. What does that say about A in terms of wavelength, so that we can really understand what happened? Yeah, it's right here. Kn is n pi over A. What does that say about the width and the wavelength? Class exercise. Derive a relationship between the width of the well, which is A, and the wavelength, because we've been using wave number a lot. It is good to also think in terms of wavelength so that we can actually plot. Sorry?
A over 2.
No, make A, express A in terms of wavelength, not just K. What together?
H bar K over wavelength.
So when we say K is wave number, what is the normal definition of wave number in terms of wavelength?
2 pi over lambda.
Absolutely. So this is equal to 2 pi over lambda. So I'm now asking, express A in terms of lambda.
2 over n lambda.
2 over,
N lambda.
correct. Yeah. Or, see, A will then be lambda over 2 pi. N lambda over 2 pi. Is that what you meant?
Yeah.
Look at it here.
Sorry.
So A will be lambda, n lambda over 2 pi. Wow.
Would it just be 2, not 2
Two,
pi?
yeah.
The
Sorry.
pies would cancel.
Pi.
Oh yeah, the pi is cancelled. Yeah. So A would be
And
n lambda. Wow, that's easy. So n lambda over 2. Wow, that's easy. Why not we just do it for the first one then? It means that when n is 1, A will be half the wavelength. Isn't that what we... That is so cool. Because then, see what we are getting. A over 2, negative A over 2, 0. We're saying that when n is 1, here is half a wavelength. No, nothing. Yeah. And the next one will then be, so the next n2 will just be the wavelength. Yeah. Yeah? We keep doing it. Yeah? Quantized and looking like things you can put in to the wave and it represents a particle. That's the cool aspect. Okay, so we take 2 minutes break and finish copy. Oh, sorry, I didn't know you didn't finish copy. A 2 minutes break, and then we do some class exercises and go into finite square world. Did you hear that? Finite square world, not just the infinite.